This conference will now be recorded.
So, Deepa, we have been discussing interference of light, and in the last lecture, if you remember, we had discussed related to interference of light. So we have learned what is called constructive interference, destructive interference, and what are the conditions for those to happen. All those things we have already learned. So today, actually, we'll be learning Young's double slit experiment, which is related to interference of light. So Young, it is Young, Thomas Young, okay, Thomas Young, who had experimentally shown during this time, around this time, experimentally he demonstrated the interference of light phenomenon. Okay, the phenomenon of interference with light has been first experimentally demonstrated by Thomas Young, and that was 18th century, 19th century. Okay, so I'll just recap what is called interference of light. When two light of waves, two light waves of same frequency and having constant phase relationship traveling in the same direction to superpose each other, intensity in the region of superposition gets redistributed, becoming maximum at some point and becoming minimum some other point. Okay, and thus a pattern of alternating dark and bright bands are produced. So this phenomenon is called interference. Okay, and it is obviously interference of light. So this we had already discussed last time, and I had shown you this figure. Okay, so you can see that there are alternating dark and bright fringes. See, this is bright, this is dark. So again, you have dark here and here bright, like that alternately, dark, bright, dark, bright. So these are called bands or fringe. These are called fringe or band. Okay, these are called fringe also, fringe. Today we'll be learning and we'll be calculating how to find out the fringe width or something like that. Okay, so let us directly go to Young's double slit experiment in detail. We'll learn here. So as you know, the conditions for the first condition for interference of light to happen, interference phenomenon to occur, what you need, first condition for interference phenomenon to occur is the coherence of the sources. This is a coherence of the wave which are interfering. And second thing is, mostly we need to use monochromatic light. Okay, monochromatic light. Okay, so see, the main challenge is to experimentally find out or produce two coherent sources of light. It is very, very difficult. It is not very easy. to find out a coherent sources of light, a pair of coherent sources of light. So there are three methods of making coherent sources of light. So methods for making coherent source of light sources. There are three actually. One is this one, Young's double slit experiment. This is a very simple way, double slit method. Okay. Then second is Lloyd's mirror and Fresnel's biprism method. Okay. So Fresnel's biprism. Two prisms will be kept back like at their bases. So these methods are not going to teach you in detail because these are not very important to learn here. In your hard classes, you will be learning how each method is doing the job of producing coherent sources. And another one is Lloyd's mirror. Lloyd's mirror. So third is Lloyd's mirror. Lloyd's mirror. Okay, there are three methods. So among them, this Young's double slit experiment is very and this setup is very simple and feasible to do in laboratory. These are also done in laboratory and these are also feasible, but this is very simple way to do. And let us see in Young's double slit how first he could produce coherent monochromatic sources. So look here what he had done. He had taken a cardboard which is made of opaque material, okay, not transparent. And then first what he had done, he had made rectangular strips like this. So this slit is known as this. Then he took another cardboard, okay, and placed a certain distance from this edge and made two parallel slits like this. Two slits, rectangular slits like this. And he kept sodium vapor lamp. Okay, sodium vapor lamp here. Okay, sodium vapor lamp which gives yellow light. Okay, yellow light. So yellow light is monochromatic light. So you have to use monochromatic light first of all to have coherent. Okay, monochromatic light. So that is here sodium vapor lamp. And then what has been done? Look, there are actually specifically this slit is, in fact, each of them, this is S1, slit S1, and this is S2. And then there was a screen kept certain distance, maybe 1 meter distance from this slit. So this distance was capital D. This is 1 meter. 1 meter. And the distance between these two slits were kept as from 2 millimeters. Okay, 2 millimeters. So this distance is actually denoted by small d. This was kept nearly 2 millimeters. Okay. So by using this method, see how it happens. See, if you keep this yellow light or sodium vapor lamp nearby, then this will act as a point source. So sodium, see wave front will be produced similar to cylindrical, or if you have cylindrical lamp, this source, then you'll have cylindrical wave front, or otherwise as a point source it will give spherical surfaces as wave front like this. It will just go through that, okay, this slit. Then see, light will go both ways, to this, even this, okay. And see, in this slit, each point on this slit, according to Huygens principle, will act as a secondary. See, this is a slit, right? This means opening or hole. Here the hole is rectangle inside. So each point on that will act as a secondary source. They will produce spherical fronts like this. Each of them will produce, and those will actually go and illuminate this slit S1, this slit S2 as well. Since the same, like the light which are illuminating this S1 and S2 slit are from the same source, so they have constant phase relationship. So the some coherent sources can be made. Okay, look in the left hand side there. See, after making the coherent sources, as you look here, so these two coherent sources S1 and S2, each point on S1 and S2 also will act as, see, if I just take a diagram like this one is this and this one is S2. So each point on there, that openings, those openings, they also will act as secondary sources, and they will actually produce oil lake, as you have learned according to Huygens principle. Those oil lakes, they will actually spread out from S1 and S2. Then while they are spreading out, look here, they will interfere each other. One from S2, another from S1 slit. They will interfere. Okay. If they interfere in phase, then what you see? You see bright fringe or bright band like this. Okay, this has been taken as dark. This is bright. So this is bright. You can see that bright band. Okay, look, and some places this overlap of the wave coming from S1 and S2 will happen, or superposition will happen in out of phase. Okay, out of phase. Then when out of phase, then the dark fringes will be created like this. Okay, so this is how the experiment was, like alternating dark and bright fringes which are produced due to interference was demonstrated by Thomas Young using this very simple arrangement of experiment. Okay, so this is actually Young's double slit experiment. So then you might be thinking, what is special this thing? What is special over here? Nothing is special. So interference. The special thing is that interference was not proved experimentally before Thomas Young. So that was the specialty. That's why he was awarded with Nobel Prize. Anyway, what we'll do here, we'll develop the theory where you have dark, bright fringes alternately. Then there is something called lateral fringe width. Lateral fringe width. Fringe width. Lateral fringe width. So what is that? This is the separation between, or the distance between. So this is denoted by, lateral fringe width is denoted by beta. That is the distance between two consecutive bright or dark fringes. You might be having some problem to understand this language, what is fringe width and all. See, fringe width, I'll show you one more figure here. You'll be able to appreciate this. See, I have this is dark, this is bright. Okay, this is again, you look, this is dark, again this is bright. So look, the separation between or the distance between two consecutive bright strings has been shown here. Consecutive, the distance between two consecutive bright strings is shown here. Look, this distance is called fringe width. Fringe width. Okay, fringe width. This is called fringe width, and it is denoted by beta. And in fact, this is called lateral fringe width. And then we will be calculating something called angular fringe width, which is this angle. You look, this see bright, there are consecutive bright fringes. So what is the, like, what is this fringe width actually making an angle? So this particular lateral fringe width is making an angle at the slit. Okay, at the slit. So that is theta. So that theta has to be calculated as angular fringe width. So there are two fringe widths, lateral fringe width and angular fringe width. So these things are the. So you might be asked to find out what is the fringe width. Yeah, what is the position? So from this fringe width and angular fringe width, we can actually locate the fringes, particular order of fringes. Okay. So what we'll do here, we'll try to find out an expression for the fringe width. Okay. We'll try to find out or derive an expression for fringe width, which is lateral fringe width. Okay. And not only that, see in this figure, this is a schematic representation of Young's double slit experiment. You look, this is the cardboard, and on which S1 and S2 two slits are made, or two openings or holes are made, and the separation between the slits are actually D. Separation between the slits are D, and this is the line which is actually, you can say this, I'll just give a name as C. So this is actually the CO line is the perpendicular bisector to this slit width. So this is called slit, sorry, not slit width. This is called, yeah, the separation between the slit. So this line CO is actually dividing this into two halves, D by 2 and D by 2. If I just give some names, suppose AC and CB here. Okay, so AC and CB, they are both, AC and CB both are of equal width, that is D by 2. All right. So my aim is to find out the fringe width. So what is the definition of the fringe width? We have seen that the fringe width is actually the separation or the distance between two consecutive dark or bright fringes. So if you want to find out that expression, like expression for general expression for beta, you must be actually knowing the position. If you don't know position of two consecutive bright fringes, then how can you find out the separation? Suppose I have beta 1 and I have beta 2. Okay, we'll just discuss it. Let me first do one thing. Let me tell you about this experiment first. What happens in case of, see, in double slit experiment, what happens? Since this C point, let us say A and this is B, the C point is central point, okay? And here the B point is the central point on the screen. sorry, O point is the central point on the screen, which is kept at D distance away from the slit. Now, since this O point is on the perpendicular bisector of the slit, the distance from S1 to S2 here, these distances are actually, see if I say SO, S1O and S2O, these distances are actually same. Okay, these distances are actually same. So when these two distances are same, then whatever light comes from S1 and S2 and meet at this point, central point on the screen, they are meeting in phase. So they are superposing or interfering in phase. Superposing in phase. So when it happens in phase, so what type of interference happens? Constructive interference happens. And you might be remembering what is constructive interference. Constructive interference, in constructive interference, the amplitude becomes maximum and hence the intensity becomes maximum. Intensity at this particular point, upon superposition of two waves from S1 and S2, the intensity will be maximum at this point O, because they are the light waves which are coming from S1 and S2 are meeting in phase. Why? Because the path there are no path differences between these two paths. Okay, yes, there are no path difference. And since these two are coherent sources they have, and they are actually coming from the same sources. These sources are S1 and S2 are illuminated as you have seen in the previous slide. They are illuminated from the same sodium paper lamp, same age, okay, from same age. That's how they have the same phase already. And only phase difference can be obtained or can be introduced by making light travel from S1 to some place and S2 to some other place on the screen where they have different paths. Obviously, so there will be path difference when light goes from S2 to P and S1 to SP. See, this S1P, this seems to be a lesser path than S2P. This is a longer path S2P. So we have to find out what is the phase difference. Okay, between the light which are going to or meeting at P from S1 and S2. Okay, so what I was trying to say is that at the central point, the bright fringe will be produced. Bright fringe, central bright is called central bright fringe. Okay, always it happens because light from the sources, both the sources are meeting in phase at the O point. This is called central bright fringe. Okay, central bright fringe. All right. So now we will be taking a general case because symmetrically, see, this is a bright central fringe, and then on either side of this O, if I take x-axis along this OP direction or this vertical line, if I take it as x direction, see both the sides. Suppose you take this as origin and then you think of this as positive x and this side as negative x. Both sides actually fringes will be produced. And see the first both sides, the first will be the dark fringe because central is bright. So alternatively, bright, dark, bright fringes will be produced both sides. But where will be bright and where will be dark? How to define or how to get this idea? Look where, see, suppose I take a very general point P, which is on the screen at x distance away from the central point. This you can just think of the origin. And from here, upward direction, let us take as positive x, okay? Positive x. Let us take that as positive x. And in fact, if you just have x, y, so it will be happening in a plane actually, in a vertical plane. So we have taken a point P, which is x distance away from the central fringe or origin also you can say, and suppose the distance between these two slits are small d, as you can see, and the light used has a single wavelength lambda. So now my question is, how do you decide or how do you understand whether this P point will be bright or dark? If we can find out the position of like consecutive dark or consecutive bright, only we'll be able to find out beta, okay, which is our aim. So for that actually we have to find out what, like at what distance dark, at what distance bright fringes may occur. So there is a condition for that, and to do that we have to use our previous classes geometry knowledge, and let us find out what is the path difference. If you ask me whether there will be a dark at P, whether there will be dark fringe or bright fringe, my answer will be what is the path difference, whether there is any path difference between these two lines S1P and S2P, whether they have some path difference. If no, then bright fringe will be occurring here or produced here. If there is phase difference, accordingly the intensity will be distributed. Okay, intensity will be according to the phase difference or path difference. Okay, so you can see that S2P is greater than S1P, right? That means there is path difference. We have to find out what is the path difference. So path difference, if we find out path difference, so path difference actually denoted by, path difference is denoted by delta. And once we find out path difference, we will be able to find out phase difference also. So phase difference, for the time being, you remember phase difference is denoted by only phi or sometimes delta phi, del phi. Okay, so there is a relationship between phi and delta, 2 pi by lambda into delta. This is the phase difference. Once you find out what is path difference delta, then it is easy to find out what is phase difference. So let us find out first what is path difference. So path difference in this case is the difference between S2P minus S1P. Okay, S1P and S2P. So what is this value? Nearly equal. You have to find out that, and then you have to see whether there will be bright fringe or dark fringe. All right, to do that we will be using our geometry knowledge. Okay, knowledge from geometry. Just a minute. So what I'm trying to do is, I'm just trying to use my geometry knowledge to find out this value. Okay. Okay, just 1 second. All right. So now let us see. We'll take a triangle PS2Q. See this triangle. This one, and this one. This triangle will take. Okay. So this is a perpendicular which I have drawn from S2 to screen, which is, then this S2Q is perpendicular to this screen. Okay. So In this case, if I want to find out what is the S to P, I can use Pythagoras theorem. S to P square is equal to, the base is actually this one. Yes, this is the base. Sorry, this is the perpendicular and this is the base. So what is the base? Look here, one thing we have already seen that this CO is the perpendicular bisector line to this slit. So slit has total width as 2D, sorry D. Then this much will be D by 2. Okay, this will be D by 2. If I just divide this D whole is D, so this is equal to dividing CO line. So this part OQ will be D by 2. Okay. Now look what we can write from here. So look, this is T square is equal to S2Q square plus QP square. Okay. And from here, S2Q actually is D square plus QP means OP plus OQ. OP is already X we have taken, and this is D by 2. So this is whole square. Okay. So now we have got equation number 1. Similarly, if we take, see this triangle, if I take another triangle PS1R. So from there, what we can write, S1P square is equal to, see S1P means this one. So this is the perpendicular D square plus this much PR square. PR square means PO minus, see this is also actually D by 2. Okay, D by 2 according to this geometry. So D by 2, so this much will be X minus D by 2. X minus D by 2 whole square. So I can write S1P here itself. S1P is equal to D square plus X minus D by 2 whole square. This is equation number 2. Now look, I have to find out what S to P. See, this one you have to find out, not square. In terms of, this is in terms of square. So S to P square minus S1P square. How do you get? You can just write down S to P plus S1P into S2P minus S1P. Okay, this I can write, doesn't matter. Okay, so look here, I'll just write S1P we have got, S1P square we have got D square plus X minus D by 2 whole square. This is equation number 1, and S2P square is equal to D square plus X plus D by 2 whole square. This is 2. Okay, so from here what we have to do, S2P square minus S1P square. Okay, so which is S1P into S2P minus S1P is equal to this difference. So if you just take the difference, this, how you get? You get X plus D by 2 whole square minus X minus D by 2 whole square. So this is nothing but 4AB, 4X D by 2. Okay, and here you get, on the left hand side, you get S2P minus S1P, which I have to find out, and this is equal to then this by S2P plus S1P. Now there is a small approximation. Look here in this figure. If this small d, that is the separation between the slit, is very less than the screen to slit distance, that means if your d and also X, the position of the fringe, dark or bright fringe, if that is mass was less than capital D, okay, then S1P nearly equal to S2P, that is nearly equal to D. Okay, so this is what we can do. We can use here it is, okay, S1P, S2P as D. So if you use that approximation, then what you get, I'll just write the approximation in the left hand side. Okay, so let me write it here. What we get, S2P minus S1P will be 4x, okay, 4D by 2x divided by here, and we have seen S1P and S2P can be written as D at what condition? At this condition. This is the approximation, okay? So with this, we will get here then to capital D, okay? So if you simplify it, you will get XD by capital D. So this is the path difference. So ultimately what we have got, X2P minus S1P, which is the path difference between the two wells, is XD by capital D. Okay? I'll write it then. S2P, S1P is equal to XD by capital D. So this is the path difference, okay, delta between the two wells. So once you get this delta, now you can compare. You know the condition for bright fringe to occur. Condition for bright fringe. Bright fringe to occur. What is that condition? Look, delta has to be m into lambda. Okay? To m into lambda. So this is actually this is the condition. Okay? So we have got so we have got the delta as xd by d, which is equal to m lambda. Okay? So from here I can find out, see this, I should write this as xm because this is the m thing in the screen by d, or m into d lambda by d. Okay, so this is actually the position. If that is the position P, if the P is the position, so which actually can be obtained as as a coordinate. As I said, that is, if you just think that this is O and this is x-axis upward, so x1, x2, x3, and all those places actually different orders of interference pattern will be created. And for bright, see m is equal to, if you put m is equal to 1, 2, 3, etc. and even m is equal to 0, see m0 corresponds to central fringe, corresponds to central bright fringe. Okay, central bright fringe. Always you have to remember that. So m equal to 0. So here m goes from 0 to all the way. Okay. So 0. So this m actually will give you the order of m, gives the order of fringes. Okay. See, like x1. This is the first. This is the second. Okay. These are the bright fringes. So first, second, all those things. Okay. So if you put the value of m, you will get the position of all the fringes. X is equal to 0. See, x is equal to 0 means at the origin. So what is that? Central fringe. Then another fringe, that is the first bright, then second bright, and in between there will be dark. Okay. So this is how we get the position of the bright fringes, and the general condition or general expression for the bright fringes is this. I'll write it here. Let me clear and line. So the position we have got xm is equal to d lambda d by small d into m. This is the position of bright fringes. M here it is actually, this is given by m bright, m order bright fringe. Similarly, if we see put this delta with 2m plus 1 into lambda by 2, this is the condition for dark fringe to occur. So condition for this we have already learned, this condition for dark fringes to occur. So this is delta is equal to 2m plus 1, where m can go all the way. See, it can go up to 0, 1, 2, 3, etc. It can go. Okay. So now look, delta we know x into d by capital D. This is equal to 2m plus 1. So this actually gives the general formula, general condition. Okay, not for this particular fringe. So look here, if I write xm, here also you will get 2m plus 1 into d lambda by 2 into small d. Now, if I just divide with the whole expression with these two, then what I get, I get m plus half into d into lambda divided by small d. So this you know already, d lambda by d. It is common for both the cases. And here actually m plus half, and here is m. So we have got the condition for, or the positions of the, so this gives the position of m order, position of mth order dark fringe. Okay, mth order dark fringe. So look what we have got. I'll just clean and write again. Xm is equal to m d lambda by d for bright. This is position for bright. Okay, and this we got m plus half d lambda by small d. So this is for dark fringes. Okay, dark fringes. Now look, if we want to find out beta fringe width, see our expression has to be like what we are trying to find out here. We are trying to find out beta. Beta means, see, if I write it bright consecutive, see the separation between consecutive bright or consecutive dark fringes. So look, I am just writing the bright. The bright I know, so this will be m plus 1 d lambda by d, and this will be m d lambda by small d. So from here it is very easy to find out after solving that this beta expression for the fringe width, this is called fringe width. And it is surprising that there is no M or N term here. That means what? Fringe width for each fringe will be equal. Okay, fringe will be equal for all of them because there is no N term here. Okay, this expression is the expression for fringe was finding out lateral fringe width for an interference pattern. Okay, for a double slit experiment. Okay, so look, this expression sometimes fringe width will be given, lambda will be given, this will be given where the screen has to be placed. Kind of that question may be asked. Sometimes capital D, screen to source distance, and the separation between the slits will be given. Fringe width will be given. You have to find out what is the wavelength used in the experiment. So this is how this is kind of expression, like from here there can be, so this using this expression actually you will be able to find out the solution for many questions. Okay, many various type of questions. Okay, so now look, so what we have got expression for lateral fringe width or simply fringe width. Whenever you say fringe width, you have to understand this is beta. Okay, expression for fringe width we have got. What is that? Beta is equal to capital D into lambda by small d. Very nice. Okay, so if suppose you are asked to find out angular fringe width, so what will you do that there? Angular fringe width. So okay, before I go there, let me handle another problem related to this. See, how would the fringe width beta change if the experiment is being carried out under the water? That means what? The same Young's double slit experiment, same experiment is being carried out inside water. So without changing any geometrical construction of the experiment, that means see, I have a slit first, yes, okay, then I have double slit, S2, and this is S1, and they have separation as D, and you have kept the screen at D distance, this is O, and this distance is D. So all things are all right. Yeah. So in the expression, beta is equal to, say, fringe width d lambda by small d. Here see, d is constant, small d is constant. So what will change here is the lambda. If you do this in any medium, not only, so the previous so this expression is actually in for air medium. If actually in general, your double slit experiment is being done in air, but suppose you do it in some other environment, suppose water. We did this experimental setup inside the water. So what will happen is actually the wavelength will change inside the water. So the same vapor lamp, sodium vapor lamp, maybe we will use in that case also. See, the wavelength inside the water will not be the same wavelength of the yellow line. It will be something else. So how to find out that change? So here, then, if you do it, see, if you find out the fringe width in the water, obviously this wavelength also has to be replaced by the wavelength of the light inside the water. Okay, so this lambda, see lambda w, how do you get? You can get it C by V water. Okay, C means what? Nu into lambda in air, which is given already, that is lambda simply, and this is actually nu lambda water. See, nu doesn't change, frequency does not change when light goes from one medium to another medium. Only changes happen in wavelength because the speed of the light changes. Okay, so you look, this is lambda in the air and this is lambda w. Okay, sorry, this is actually, see, due to the refractive index, this is actually refractive index, sorry. This is a refractive index. From this definition, we can find out what is the relation between this delta lambda or the wavelength in the water. Okay, so wavelength in the water you will find as lambda by mu, or in other words, the wavelength of water inside the water will be equal to lambda by mu. Lambda by mu. That means you have to replace the lambda with lambda by mu. Okay, lambda, the wavelength of the light in the air itself, 45 was given, and see the mu also will be given. Refractive index of the water also will be given. So there you can just simply write this. So do you understand that if the Young's double slit experiment is being carried out under water, your fringe width is going to change d lambda by mu into d. So this will be the expression, mu expression. Okay, underwater. This is underwater. And in air, what was the expression? In air, simply this, d lambda by d, capital D lambda by small d. Okay, so this is the important concept which may be useful for you to solve various problems. Okay, now I will just do one thing. I'll just find out the expression for the angular fringe width first, and then if time passes, maybe 2-3 minutes or maybe 5 minutes, I'll take extra and I'll discuss one more good point. Okay, look, as I was discussing what is called angular fringe width, that is denoted by theta. Angular fringe width is denoted by theta. Sometimes there will be numerical problem in exam from this particular problem. See, if I write tan theta, what you can write from this geometry? This is nothing but beta, and this is capital D. So what I can write is beta by capital D. Okay, perpendicular by this. Okay, theta means. If this theta is very, very small, if theta is small, for small angle approximation, what we can do? Theta is equal to beta by del D, and we have found out the expression for beta, that is d lambda by small d. Okay, divided by d. D goes up, and you get finally lambda by small d. That means the wavelength you have used and separation between the slits depends on the angular displacement. Sorry, angular with theta, that depends on lambda by d. Okay, lambda is the wavelength of the light used, and d is the slit separation. Okay, so this is actually the expression for angular width. So what we have learned today, we have already learned Young's double slit experiment, and then we have found out the expression for beta, expression for theta also. This is by, yeah, so this is d lambda by small d. If this is done in water, then mu water. Like see, just this expression, whole expression will be divided by mu. That's all. Okay, so these are the things we have learned. I'll quickly discuss this point and then I will just stop the class. Look, we have seen that in young double-slit experiment, two light bulbs from S1 and S2, they interfere at any point of the screen, and alternatingly you will get dark and bright fringes. Okay, that depends on how these two lights are meeting, whether they are in phase or out of phase. But anyway, the central point of the screen, which will be always bright, always bright, okay, always bright. And see, this bright fringe, central fringe, whether it will be always remaining at the center or at what condition this central fringe will like get shifted or something like that. Okay, so here we are taking one situation. Suppose a glass piece, a glass of refractive index mu and thickness T is placed in front of S1. So what does this mean? This means that the light wave is not completely moving up to P from the source S1 in air. So some part is air, and some part in glass. Okay. Now this is actually the case. So I'll tell you one thing. If both the lights are traveling in air, then their path difference will be just S2P minus S1P. But when one of them travels through certain medium of having certain thickness T and refractive index mu, which is greater than this mu is greater than 1, in that case, the path difference is not only, so path difference delta is not only S2P, it is not only S2P minus S1P, because this path S1P is not correct now. So what is the path you are this light travel then? Or in other words, what will be the path difference introduced in this? How much extra path difference will be introduced by this glass? You have to find out. See, in air we had got the path difference xd by capital D. So this much path difference was there. Now some path difference will be again introduced to this S1P. The S1P path will not be just S1P. It is S1P plus some path, which is actually travels inside the glass. Generally, it is written as mu into T. This was path. If you just simply passing through a material having this mu refractive index mu and thickness T, then path will be added actually mu into T. But what is the path difference? Path difference introduced. Path difference will be actually, see, you have to write path difference, extra path difference, suppose delta P, okay, del delta, suppose that one. Okay, so this you have to write path travel in the glass minus path travel in air. Okay, so this will give you actually, see, if you want to find out path difference while passing through this glass, then you have to write the path inside the glass is mu into t, this much distance. And if the glass was not there, or refractive index just mu is equal to 1 of thin thickness material, so the path in air will be t. So ultimately you will get the path difference as mu minus 1 into t. Okay, this will be your path difference. So what we have got, that extra path difference which is added here is this much. Okay, all right. So this is with S1P. Okay, now we have got, so this is S1P square, this much plus, see whatever we had, d square plus x minus d by 2 whole square. Along with that, this also will be added. Look, this was already d square plus x plus d by 2 whole square. Now, if you do this same calculation, if you do, you look that these two, anyway, from here you will get xd by capital D and minus of this mu minus 1 into t. So this much extra path difference you will get. Okay, all right. But you know, you will be asked to find out what is going to happen here due to this path difference. Actually, look, this path difference is actually natural. This is not due to the path, like due to going from where to where. Even if it is going, see, if it is going to central point C and it passes through this glass, then also this much path difference will be introduced. Okay, so in general, at the central bright fringe there will be no path difference. So look, if that to happen, your fringe pattern or central fringe has to be shifted somewhere. Look, this I can just put it to 0. Okay, so you will find out this x central fringe x0 I'll write. This will be mu minus 1 into t into capital D by small d. So this much distance it will be shifted. Okay, this much distance it will be shifted. Okay, and we have found out the expression for beta as well. So look, what we can do is we can write this shift in terms of beta. See, d lambda by d is beta. So capital D by d will be beta by lambda. Okay, so this will be beta by lambda, d by d. So if we replace it here, you will get mu minus 1, okay, into t into beta by lambda. So what do you mean by that? So the central fringe will be actually shifted to a position which is given by mu minus 1 into t into beta by divided by lambda. Okay, so this much shift will be there in the fringe pattern. Not only the central fringe, the whole fringe pattern itself will shift by this much distance. Okay, so fringe pattern will be shifted. Fringe pattern will be shifted if one of them actually in front of one of them a glass having a refractive index mu and thickness p is kept. So will be shifted by x naught is equal to mu minus 1 into t into beta divided by lambda. This much distance. Okay. So I hope you have understood this. If you have not understood, then you can ask me or you can ask me in other classes also, doesn't matter. So is it all right for you? Do you understand everything what I have taught you today? Deepa? If suppose one among them is just block, then what you see? Do you see any fringe pattern? No fringe pattern. No fringe pattern will be seen. Okay? If one among them is block, then there will be no interference pattern. Okay? So that's why no fringe pattern is no fringe pattern if one of S1 or S2 is blocked. Okay. So okay. So with this we will stop it here. Deepa, I hope you have understood this. If not, you can ask me again. Do you have any questions or doubts? See, if not, then I'll stop it here for today. If you have any questions at all, you can ask me some other sessions also, future sessions also you can
No,
ask.
sir.
Yeah, you are saying something, Deepa. You have any doubt? Okay, then I'll stop it here.